Please welcome Senior Research Scientist at Expedition Technology, Mr. Enrico Mattei.
I appreciate the opportunity to talk to you today about RF machine learning systems, or RFMLs, where we are at the intersection of signal processing and machine learning in order to better secure the Internet of Things. So I want you to consider a situation like this where we have a man-in-the-middle attack where the wireless access point is looking for a particular MAC address, or in general, a digital ID, that an authorized user presents to gain access to the network. However, this is very easy to spoof and steal MAC addresses by a man in the middle. In this scenario, the unauthorized user can present the stolen digital ID to the wireless access point and gain access to the network. What we want to do on this program is that we want to enhance existing authentication methods with an RF device-specific fingerprint in such a way that in this scenario now, the man in the middle not only has to steal the digital ID, he would also need to steal the physical device, and I'm sure you agree that that's much difficult to accomplish. And just to put it in context, such a similar attack like this one that I'm showing you here left the majority of the United States East Coast without internet access in 2016. So it is a very relevant problem. These device fingerprints are generated at the transmitter. So I'm showing you here how a typical IoT device transmitter looks like, where we have a communications modulator that takes a digital signal, and a digital signal here is nothing more than a sequence of bits. Now, the communications modulator outputs a sequence of what is now symbols. And think about symbols as just groups of bits. So if we group bits by force, then the modulator can only output 16 different symbols. Okay? So it outputs a sequence of symbols as two orthogonal signals. Now, this is very important now because at this point, these two orthogonal signals can be interpreted and manipulated as one complex value signal, okay? Where each symbol now is a point in a complex plane. So at this point, we're still in the digital domain. We need to go and convert this digital signal to an analog domain such that they can be sent out through the antenna. So they go through digital to analog conversion, and they are used to modulate two orthogonal RF carriers. And these RF carriers are usually at radio frequencies. So think about megahertz, for instance, in a way that we can transmit information. So let me go back to the modulator. Here I'm showing you a complex plane with all possible symbols allowed by a particular modulation scheme. Now, each symbol has a magnitude and has a phase angle given by its coordinates in this plane. And so what happens when we transmit a symbol, A1, is that the amplitude and the phase of these RF carriers changes according to the amplitude and the phase of this particular symbol. And when we transition to a second symbol, A2, then the magnitude and the phase of the RF carriers changes according to the particular symbol that we are transmitting. And this, in general, is how information is transmitted over the air. So what happens when a device transmits a sequence of symbols? Remember now, a sequence of symbols is a signal. So as the signal transitions from symbol to symbol, it traces out a path in this complex plane. So now imagine that a second device now wants to transmit the exact same sequence of symbols. So he stole my MAC address or digital ID and is trying to gain access to the network. What happens is that because of these hardware imperfections, his signal traces out a slightly different path in the complex plane. And these are the differences that allow us to discriminate between these two devices. These differences are introduced at the hardware level in the digital to analog conversion process. Why? Because these are analog circuits that are designed to a specification. However, the manufacturing process is not perfect, and it introduces random deviations from the specification. So what that means is that no two circuits are identical, and therefore no two devices are identical. So today, and it is the year 2019, this is still done by hand designing features. Okay, so we have a communication signal processing expert looking at signal types and modulation schemes and handcrafting features that allows him to be able to discriminate between devices. Now, obviously, this is the IoT. This cannot scale. If anything changes, we need to go back to the drawing board. So this is where machine learning comes in to help us scale this to a large number of devices that are required by an application such as the IoT in a way that is efficient by learning from large amounts of training data. Now, when we talk about machine learning today, immediately what comes to your mind might be something like computer vision. And allow me to show you the differences between images and RF signals. So if I show you these two animals, visual inspection will allow you to quickly determine that these two are different animals. I'm showing you a cheetah on the left and a leopard on the right. However, if I now show you this, could you tell the difference? I think the answer will be no. These are two signals from two different devices. So surely they must be different. But remember that they are transmitting the exact same sequence of symbols, exact same data. Okay? So this is the amplitude spectrogram of the signals. And if I showed you the phase, there are differences here. However, I think that visual inspection will not allow you to determine these differences. So we need to dig a little bit deeper. So how about if I showed you the difference in the phase of these two signals? So now we can start to see some differences between the two devices popping up. This is absolute phase, so bright means very different. Okay? So there are differences in the phase. The phase matters. However, note that the differences are, in general, very sparse. So phase matters for RF, and phase matters for images as well. Phase in images carries information about edges, textures, and image detail in general. Phase is related to frequencies, and frequencies and high frequencies represent edges in images, right? So let me show you. Let me tell you what I did here. So this is to illustrate that point. I took the image of Einstein that's on the top. I computed his discrete Fourier transform. I took the coefficients of the Fourier transform, which are complex valued numbers, and I did two things. First, I preserved the original phase of the coefficients, and I perturbed their amplitude. And I reconstructed the image from those coefficients, and I'm showing you the result in the lower left. Second thing I did, I took the Fourier coefficients, I preserved their magnitude intact, and I perturbed their phase. And I reconstructed the image from those coefficients. And I'm showing you the result on the bottom right. So clearly, inappropriately manipulating the phase destroys image content. However, note that this is now more relevant when we're doing spectral processing versus the spatial type of processing that is done by modern deep learning architectures such as CNNs. But fact remains that phase is important for images as well. So now how can we take our complex value signals and process them through neural networks? So there are two approaches. One is very simple, in which we say, well, we're just going to ignore the face, right? So we take the complex signal and just treat it as a real valued signal. In this case, we can process it through a real valued neural network to a real valued activation function, such as a rectified linear unit. However, I just mentioned that face is important. There's information in the face. Differences between devices are contained in the face. So the better approach, an approach that is better than real, would be to actually have a neural network that has complex valued weights. In this case, we can do complex valued mathematics and backpropagation into a complex valued activation function. So an activation function that takes a complex number and attenuates its magnitude as a function of its phase, preserves the original phase intact. This is called a cardioid activation function, which was originally proposed by Stella Yu, which is our academic partner on this program. This activation function has a very nice characteristic that, if you note on the real line, it reduces to a standard value common in real value deep learning. Okay, so now we have the tools and we can put this to work. Our architecture is a variational autoencoder, and what this does is just simply takes an input signal, it compresses it down to a more compact, low-dimensional representation that still preserves enough information about the input in order to be able to reconstruct it. So it is encoded into a low-dimensional representation and decoded back to the original dimensionality. Now these low-dimensional representations we interpret as our device fingerprints. This is where we do classification. So one more thing, here we impose some prior knowledge. So we're going to structure this device fingerprint space in a way that makes sense for the problem that we're solving. And the structure that we're going to impose is a Gaussian mixer structure in this space, where each Gaussian component corresponds to a particular device in the training set. Okay, so each cluster represents a device. And in order to train this is very simple. You take the input, compress it down to this device fingerprint, reconstruct it, measure the error signal from input to reconstruction, minimize this error signal, while at the same time enforcing this Gaussian mixture constraint. Okay, so now we have this working. Let me show you some results. I'm going to show you now some results of 3 experiments. And each experiment was run twice with the same architecture. The only difference between the experiments is that the first time it was run with a network that had real valued weights. The second time it was run with a network that had complex valued weights. Here we have classification accuracy on the y-axis. In blue, we have the results of our real valued network. In orange, we have the results of our complex valued network. The 3 experiments were designed such that they increase in difficulty as we go from left to right, in the sense that the first experiment on the left is our standard machine learning problem, where we have our data in one bucket and we randomly split that data into a training set and a testing set. And that's the first experiment on the left. The second experiment in the middle, we had now 2 buckets. We started out with 2 buckets. The training bucket had data that had a low noise level, so it had high signal-to-noise ratio. And the test data was selected such that it had higher noise levels, so it had lower signal-to-noise ratio. So now we see that the statistics between the train and test sets are becoming different. The third experiment on the right was slightly different. Here we collected training data that was recorded in an indoors environment. Now think about this as an office environment where you have multiple echoes that are corrupting the signal that gets recorded. And the test data was collected outdoors in a completely different RF propagation environment. Okay, so what I want you to note here is not the absolute numbers that I'm showing you. Those are there for reference. I want you to notice the deltas between the blue bars and the corresponding orange bars. What this is telling us is that for this application, as the statistics of the train and the test set become different, the complex valued networks are able to generalize much better. So this is all great, but are we done? We're not done. Why? Because this still is assuming that the underlying geometry of the space of complex numbers is Euclidean. However, we know that that is not true. The underlying geometry of the space of complex numbers is a Riemannian manifold, which is a special type of non-Euclidean space. So our academic partner, Stella Yu, is working on designing processing layers that exploit this underlying geometry of the space of complex numbers. And the question that we are asking is there anything to be gained if we have processing layers that are well matched to the type of data that they are processing? The answer seems to be yes. Here we have, I'm showing you two charts, classification error on the left and number of network parameters on the right. The task is automatic target recognition from complex valued SAR images. Now note that we have in blue the results of a standard convolutional neural network baseline, such as a VGG19 type of network. And in green, we have the results of a neural network that was composed by these new geometric layers. So note that we are able to maintain or reduce the error rate, while at the same time drastically reducing the number of parameters in the network. What is this saying? This is saying simply that when you have processing that is well matched to the data that you are working with, then you are able to gain efficiency by eliminating redundancy, pretty much. We are able to train much more efficient networks in terms of number of parameters. I want to leave you with this message. RF machine learning has a very important application in enhancing the security of the IoT, where current approaches cannot scale to meet the demands that this application requires. That as the train and test set statistics become different in our application, complex valued networks tend to generalize much better. In addition, if we are able to design processing layers that exploit the intrinsic geometry of the input data that they are processing, we are able to gain efficiency by eliminating redundancy in the network. And the impact of this is that we are able to take this technology from the lab, where it is today, into the wireless access points at the edge to better secure the networks that we have today. So I think that concludes my talk. I thank you very much for your attention. Thank you. Okay. So I have a few questions. Question number 1. How unique is a device's fingerprint? Does a standard IoT device have the bandwidth, SNR, linearity, etc., to be able to perform the fingerprinting you describe, or does it require a specialized receiver? Okay, so let me start with the first question. How unique is a device fingerprint? A device fingerprint is unique it's a function of the tolerance of the manufacturing process. So if these random deviations that the manufacturing process imparts in these analog circuits, or the digital to analog converters, is small, then this problem becomes harder. Okay? So, however, IoT devices are cheap. So we cannot afford to put expensive components in these devices. So cheap components have higher tolerances. So these devices are, we are able to separate these devices very well. Device fingerprints are unique. I will say that it is a function of the type of receiver that you collect the data with, as well as the propagation environment. Does a standard IoT device have the bandwidth, signal-to-noise ratio, linearity, etc., to be able to perform the fingerprinting you described? Or does it require a specialized receiver? So the receiver is independent of the IoT device. So the receiver in this case will be, think about the router, right? So IoT signals, think about Wi-Fi, may have a 20 megahertz bandwidth, and these routers are designed to receive these signals. So yes, the received hardware has what it needs to be able to discriminate between these two devices. Are the fingerprints stored anywhere? If so, how are they secured to prevent compromise? So the fingerprints aren't stored anywhere. What we stored are the model weights. Okay, so we take the signal, we encode it, we extract what we call the fingerprint, the low-dimensional representation, and we classify. Right? The signal is not stored, the fingerprints aren't stored. Third question. What is the reason why complex valued networks seem to outperform their real valued counterparts under challenging scenarios? It's a very good question. So I'll say that having complex valued representations inside the network, not only the weights are complex valued, remember the data are complex valued, so all the activations in the network are complex valued. So even down to the device fingerprint, we have complex value representations. Now, in this case, what happens is that when we have complex value representations, we are able to coherently integrate over these signals in order to gain average out the noise and the propagation channel degradations in a better way as if we're doing real value processing. So coherent processing means that noise gets averaged out and the signal gets increased in power. So that is, I believe, what is allowing these complex valued networks to perform better under the more challenging conditions. Those are all my questions. Thank you.